Greetings, everybody. I'm waiting a few minutes. I have two viewers, it looks like. If somebody's present, please send a question and let me know you're here. I'll wait for a few people to get started. There we go. Brian, greetings. Excuse me. Three viewers. Okay, people are showing up slowly. I'll give people another minute or two, and I'll get started. All right, I'm going to get started. At the moment I see Brian is here, someone else, but I'll just assume you're out there in cyberspace. This is Atlas training session number 3, and today I'm going to talk mainly about KGB, which is the math behind, which is KGB is shorthand for k-orbits on G mod B. And this is really the heart of the Atlas software, and it requires some explanation and a little bit of getting used to. Once you do that, that you have a big leg up on understanding how the software works. So that's the main goal today. I want to talk about KGB and then use that to talk about discrete series representations. That's the last time I talked about principal series, and the other extreme is discrete series. And there, some of the issues, I just realized that my table is shaking and it looks like there's an earthquake here. What was I saying? The discrete series is sort of the opposite case of principal series, and there some issues there that are, rather different. And then the general case is a combination of the two. So once you've gotten your brain around principal series and discrete series, you're well on your way to the general case. Okay. So I want to start off with just a couple of things about the software. So the first thing I wanted to do is mention that the recommended way to hang on a second, let me go back over here. Really, the recommended way to stay up to date with the software is using Git. And Git is software. It's a system for maintaining software. We're using it for the Atlas software. And the advantage of it is that the latest version is always available by Git, even if I haven't spent the time to package it up and put it on the Atlas website. And even if I have, sometimes it's more convenient to use Git. So let me just show you very briefly how it works. Git runs on all computers. If you don't have it, it should be easy to install. And for example, I'm in my software directory, and if I do git branch, for example, I'll see that I'm on what's called the master branch of the software. And if I do git log, I see a record of changes to the software. Now, if you've been downloading the software from the website, you won't see this. There's no record of this there. But here you can see that Mark made some changes in the install. I made some changes in the AT files. There was a merge. There was some changes recently. Anyway, that's the there's a record of that here, And when you want to get the latest version of the software, what you do is git pull origin master. And that says that get the latest version of the software from the origin, which is on the version of the software stored on GitHub, and master is the branch that we're on. And well, in my case, it's already up to date, but if it wasn't, it would have sort of seamlessly updated the software to the latest version. So there's some instructions on how to use that on the Atlas website. I recommend you do that. Okay, that's Git. All right, let's go back now. And hello, Susanna and Brian. Good. Let's go back now to a different window. Hello there. And I want to look at, what do I want to look at now? I want to look at a terminal window, I think. Here we are. Okay, so let's look at Atlas. Okay, so before we get started on the math, I wanted to talk about a few things about the software and syntax and so on. So first of all, I've talked about this before. Let's say I've talked about using set. So typical thing is you say set x is equal to 1. And you notice here it said hiding previous one of type something or other. And so actually, to make this clean, I should quit and start over. Let's try that. So now you've just started the software. You haven't loaded anything except for basic, which gets loaded automatically. And now I'm going to say set x is equal to 1. And I've set x to be the integer 1. And in the past, I've often done the following. If I wanted to use x to be something different, I said set x is equal to 2. And notice it says hiding previous one of type int. And Mark has told me that this is not really a good idea. The better thing to do, if you have a variable that's been defined, such as x, after the first time when you set it, after that you can reset it using this colon syntax. And one advantage of the colon syntax is you don't get this annoying hiding previous one of type int message. But there are other reasons having to do with the software, which makes using the syntax better. So my fingers are kind of programmed to use set, and it's a little bit hard for me to change, but I'm going to try and mend my ways according to Mark's instructions and use this colon syntax. Okay, now if you have a variable that hasn't been set, for example, if you say y, if you try and use that for y, you get an error. So you have to first set y, and then you can use the syntax. Okay. All right. So another thing I wanted to do is show you something about rational matrices. So last time I talked about the change of basis stuff, and for that I wrote in a T file, the coordinates file for doing that. And in doing so, I used some rational matrices. And since then, in talking to Mark, I've cleaned that up, and Mark had already implemented some things. Anyway, to make a long story short, rational matrices are now better incorporated into software than they used to be. And so let me just show you a couple of examples of that. So let's take a matrix. For example, the matrix 2, 1, 0, 1. Oops, let's make that equal to a matrix. And integral matrices have always been fine. You can look at them just by typing A to see the matrix as a matrix. And you can do things with it. So you can multiply vectors, for example. And now, what about rational matrices? Well, so for an example, I mentioned last time, what if I tried to compute the inverse of A? Well, I get an error because it's not invertible over the integers. And last time I mentioned a different command called invert, but now there's a better command called rational inverse. So I'm going to set B to be the rational inverse of it. Whoops. Okay, now I realize I forgot to load the necessary files. So all of this is defined in the file rat.mat. So I'll load that. And now I have this command rational inverse. And what is B? Well, B is a rational matrix. Let's check. And a rational matrix, it's shorthand for a triple consisting of matrix and a string, which is just the division sign, and an integer. And what this stands for is the matrix is integral, and then you're dividing the whole matrix by 2. And it doesn't look that nice to just look at it that way, but there's a command called show, and it shows this matrix as a rational matrix. The spacing isn't so great, but you can see that's the rational matrix B, and you can multiply a rational matrix times an ordinary matrix, and you get the identity. And let's just see that it really is the identity. It is. And if you have a, let's set C is equal to B times A. C is a rational matrix, but of course the denominator is 1, so it's really an integral matrix, and you can convert it. You can say rat.mat as mat of C, and that's an actual integral matrix. Okay, and you can do things with rational matrices, like, for example, if B is this rational matrix, I can act on rational vectors in the obvious way. Okay, all right, so that's just some convenient stuff about rational matrices. Okay, now there's one other thing I want to talk about the syntax in the software, and that's the following. So there's some syntax which goes as follows. For example, you can say x is equal to 2, say, and then you can compute, for example, x cubed, and that returns 8. Now, there are local variables. So x is now, x is 2, x cubed is 8, and I can set y is equal to x cubed, for example, so that y is equal to 8. Now there's a local variables way to do this, which is the following. Let's let a be 2 in a cubed. Okay, so this is the key bit of syntax in this software, which might look a little unfamiliar. So the idea is you have this function a cubed, or x cubed, say, the function cubed, and you want to evaluate it at 2. So the way you do it is you let a be 2 in the function a cubed, and you get 8. And a is a local variable, which is to say it was set equal to 2, but then it went away at the end of the expression. Okay, and this is very common syntax. You will use local variables which appear and then disappear because there's no point in keeping them around. Okay, so let's do a couple other examples of that. So just to do a slightly more complicated example, you can say let a is equal to 2 in quadratic 3 times a squared plus 4 times a plus 1 is 21. And it's returning this value. So I can set b is equal to this, and I get b. Okay. Now, you can string these things together as follows. I can say, for example, let's let a is equal to 2 in. Now I can put another expression here, and it can be another let expression. So for example, let b is equal to 3 in a to the b. Okay, so that clearly is going to evaluate plug in A is equal to 2 and B is equal to 3 and return 8. All right. And this syntax gets used a lot. Let me just string one more together just for fun. And let C is equal to 4 in A times B times C. Okay. And this in let, in this, if you look in the AT files, for example, you'll see strings of these expressions. To make things a little more readable, there are a couple of other ways of doing that. And a synonym for in let is then. So you say let it A is equal to 2, then B is equal to 3, then C is equal to 4 in the expression A times B times C. Okay, and these these strings of lets always have to get terminated with an in. So, for example, if you say let A is equal to 2, let's see how do I do it. A is equal to 2, and then if I hit return, I get an L here indicating that I'm within one of these let statements. And I can say in let B is equal to 3. And let's say in A to the B. So so the software, if you're typing things on the command line like this, this L at the beginning will keep track of the where you are in terms of nested expressions, and sometimes it can get pretty complicated. I won't do a complicated one here, but just show you that this is a feature. Okay, so let's go back and say A is equal to 2, then B is equal to 3, then C is equal to 4, and A times B times C. And let me remind you, I can capture that by saying set D is equal to this. And with a set command, you don't need an in at the other end. So that's that. And another way, an equivalent way of doing this is the following. You can say let A is equal to 2, comma, B is equal to 3 in A to the B. That's another way. So in let or then or comma all have the same effect. Now, another related piece of syntax is the semicolon. And what the semicolon does is it terminates the expression, and will if you have several expressions with semicolons in between, the return value is the last one. So let's just look at that. Let's say, what is x? X is 2. And y is 8. So what is x semicolon y? That's 8. It's kind of a silly example, but it just shows that if you, when you string these things together, what gets returned is the very last one. And an example of this is the following. You can say let x is equal to 1 in. Let's say let y is equal, let x is equal to 2 and let y is equal to 3 in x to the y. And then if I put a semicolon here, that terminates that expression, and x plus y at the end. Is this going to work? I forget. Let's try it. 5. There you go. So the x to the y gets thrown away in effect, and what gets returned is x plus y. And I'll give you another application of this. Let's look at, often it's useful to put in print statements, for print S more precisely. So let's say print S, for example, hello world. It prints that. And what's the return value here? Let's set, let's do X, well, not X. Let's set R is equal to this, R is void. So the print or the printS command returns type void. And so, for example, what you can do is in an expression like this, you can put in a print command, for example, print s x equals x, y equals y, semicolon, and this whole thing is returning void, and so as far as the expression is going, isn't really doing anything, and then you can put your x to the y. And so it just puts this print statement in the middle, and it says when it evaluates it, it puts in the print x is equal to 2, y is equal to 3. It still returns the same value of 8. So if you look in the script, you'll often see these printS statements sprinkled in various places with semicolons after them, and that's why. That's how that works. So here's another example. If I wanted to do it this way, I could put 2 print statements separated with a semicolon, and that would put a line feed in between them. And again, the value that's returned is the one at the very end. Okay, I see a question. Sorry, I missed it earlier. So the B already defined does not interfere with the B in the let syntax. Well, I forget which B I was talking about, but presumably the answer is yes, that's correct. Let's do an example of that. Let's set C is equal to 1. C is 1. And then let's let C is equal to 3 in C times C. It returns 9, and C is still 1. So this C inside the let is a purely local variable and doesn't interact with anything outside it. Okay. All right. Now another place where this kind of syntax occurs is in for statements. So let's do an example of that. So the standard thing is to do, for example, for I colon 4 do I, and that says that it runs for to run over I from 0 to 3. And well, since it's doing I, it's for each of those, it's returning the value I, and you have to end this with odd to terminate it, and it returns the string, the array 0, 1, 2, 3. Or for example, if I said 2 times I plus 1, I would get the string of odd integers. Okay, now this often gets used as follows. Let's set V is equal to an empty array, and now let's do for I colon 4 do V colon equals 2 times I plus 1 odd. Okay, so what does this do? It says runs over I, and then for each I, this V sharp means append the right hand of the equal sign to V. And so it's going to append each of these numbers to V one at a time. And the odd terminates the for loop. So this loop will run, and let's see what happens. So that's interesting. The return value of this loop is a little weird. It's an array of strings. And well, I don't care that much. The point is V has now become 1, 3, 5, 7. So let me do that again in a slightly different way. So let's initialize V to be empty. And then what I want to do is I run over this for loop, and I don't care about the return value of the for loop. That was this weird thing. So I just terminate this with a semicolon and say what I'm really interested in is V. And that returns the 1, 3, 5, 7 that I'm interested in. So for example, I could say let W be this thing, or sorry, set W to be this. and I get W. And what happened there? Well, it ran a second time. If I do it again, it'll tack on 4 more. Okay, so and just one last thing. Let's say let's do V. Let's not initialize V again, and let's run this command. Another way to do this would be the following. Let's let some dummy variable A is equal to this in A. Now, what does that do? It says it runs this, in V. It runs this loop, it sets it to be A, and then that at the end I say in V, and it will just return V for me. So one of the things that I often get a little bit confused with the software writing it, and you'll see this if you're looking at the scripts, is there'll be long sequences of expressions, and they terminate either with a semicolon or with an in, and it depends a little bit how they're written. Okay. All right, let me pause there, see if there are any questions, and I'll go on to talk about KGB. Alrighty. So let's see, where am I? So let's make sure I've loaded everything I need. Did I load all? I didn't. Now there's a couple of other files that you might be interested in loading. One of them is all parameters. This one isn't loaded by all at the moment. This is a fairly new file. And there we go. Okay, so before I turn to KGB, I want to do a couple more examples of minimal principal series and things like what we did last time. And there's a couple of new commands along these lines which are helpful. So in particular, there's this command. Let's first do minimal, let's set G is equal to SP4R. And let's look at the command minimal principal series. And remember, you need a question mark at the end when you're doing what type of a command. And the syntax is you give it a pair of rational vectors and you'll get a parameter. And so that's the first version is the one I'm interested in. So let's do a minimal principal series of G with row of G, row of G. That's familiar one. That's the parameter for the trivial representation. And well, you can put in different things. For example, I could have set new to be 0, 0 instead. And now there's some of these all commands which are handy. So let's look at all minimal principal series. And you hand it a real form and a rational vector, and it returns a list of parameters. So, and let's see, there's another one which is all minimal. Oops. Sorry, that's the command I wanted to show. So let's set PS is equal to all minimal principal series of G at row. Okay, so for P and PS to print this P. Okay, so these are the 4 principal series of SP4 at infinitesimal character row. And you see, of course, that the news are all the same, and the lambdas are the 4 possible lambdas mod in X upper star mod 2X upper star. Okay. And well, I showed this command last time, but what's happened since last time is I improved it. It only worked in certain settings before, and now it's much better. So let me do a couple of other examples. let's set G is equal to GL2R, for example, and take all the minimal principal series of G. How many are there? There's 4. Let's print them. So these are the 4 principal series of GL2 at rho, and that's not that different, except that this command didn't used to work because this group is reductive. Another example is it's reductive and not semi-simple. This command doesn't require the group to be split. Let's say G is equal to U22, for example. And let's take all of the minimal principal series of G. How many are there? 3. Let's print them. So these are the 3 minimal principal series of the group U22. Now, the cartons of U22 are all connected. Let's set P is equal to the first guy here. Oops, I haven't set it. Set P is equal to the first fellow here. And let's set H is equal to the carton of P. And print carton info of H. So this is the most split carton in U22. It has no split factors and no compact factors. It's just 2 C crosses. So in fact, it's connected. But nevertheless, this group has 3 minimal principal series, not coming from the disconnectedness of the carton, but coming from the Weil group. And I'll talk about that a little bit later and see where that comes from. Another thing we can do now is there's a command all parameters carton gamma. You hand it a carton or a carton class, a real form and a rational vector, and what you get back is all of the parameters with that infinitesimal character coming from that carton. Okay, so let's set G is equal to SP for R, and let's set H to be the carton class of G numbered 1. So which carton is this? This is the carton with a C cross in it. And it's just a C cross. And let's set params is equal to all parameters carton gamma, HG rho of G. So how many parameters are there here? Just 2. There they are. And finally, I'll do one last example. If you set H to be the carton class number 2, and we look at all of the parameters coming from that carton, turns out there's 8, which is sort of interesting. And there they are. So one of the nice things about this is if you're interested in some representation, some parameter, and you create it and you're sort of want to study it, one thing you can do is look at other parameters which are similar coming from the same carton. And that reminds me of one other command which is useful, which is the following. Let's set P to be the last fellow of this list. There's P, and let's look at all parameters of P. What do I want to call this? Others. So this is what this does. All parameters of P, what this gives you is all of the parameters with the same differential. So this Cartan has two connected components, and that says that if you hand me a parameter for this Cartan, the total number of parameters with the same differential is 2, and here they are. So again, that's something that's quite helpful to do when you're trying to understand what these parameters mean. All righty, let me pause there, and then I'm going to turn the next. Now I'm ready to talk about KGB, unless there are some questions before I go on. Nothing. Okay. So, well, please chime in with any questions you have. I'm going to go back now to a different page. So let's go to the PDF. Okay. So here we are. So I apologize. I'm sort of giving a math talk now, but I feel it's necessary. This KGB stuff is subtle and important and interesting. So I'm going to take a few minutes to explain it. Probably this will take me to the end of the first hour, and then I'll take a break and then use the software to look at examples. Okay, so I'm going to remind you what we did last time. I talked about parameters, a parameter being a triple x lambda and nu, and sorry, I'm not in the right place to make that happen. Let's go here. Okay, so so x lambda nu. So x is an element of this KGB space. It's a k orbit on G mod b, and this is what I've been avoiding talking about. So I'm still, for now, I'm still going to avoid it. I'm just going to say that so far what we know is that given one of these things, we get a theta x, and which is an involution of the Cartan, and lambda is an element of this lattice x upper star modulo 1 minus theta x upper star. And last time I think I punted a little bit on this technical point that it's actually in x upper star plus rho. If the group is semi-simple and simply connected, then rho, you can ignore it, but in general, you need it. In any event, lambda is an element of this shifted lattice, modulo 1 minus theta. And I mentioned that nu is here. So nu x upper star sub q is x upper star tensored with q. And nu is in this quotient of this modulo 1 plus theta x times itself. And since this is a vector space, this can be simplified to just be this x upper star upper minus theta. And I mentioned that last time. I usually talked about nu as being an element. Whoops. Go up here. I talked about nu as being an element of this subspace, but you can also think of it as being an element of this quotient. And the infinitesimal character of the corresponding representation is always this expression 1 plus theta over 2 lambda plus 1 minus theta over 2 nu. And since I'm always taking nu to be fixed by minus theta, that can be written this way. Okay, so roughly speaking, as I mentioned last time, this x is giving you a Cartan or a Cartan subgroup H, or a conjugacy class of Cartan subgroups. And well, the simplest thing to say is that the Cartan involution of this real Cartan is given by theta x. And last time I focused on the case where theta x is acting by -1, which corresponds to this Cartan being split. And when that happens, this lambda is an element of this quotient of x upper star modulo 2 times itself. I forgot to put in the plus rho here. And what you're getting is a character of the compact part of this thing, which is this product of Z2s. And now that I've written this down, I realize that there is a technical point here which I'm Glossing over, which is if rho is not in X upper star, then there's some covering issue here. Well, actually, I'll say, I can say something about that in a second. This nu is of course an element of this tensor product space, of this rational space, and then you're constructing this induced representation from some character, and the character that you're inducing is this one, rho minus lambda. Okay, so issues about rho not, well, so I said that lambda is required to be in X upper star plus rho, which says that this difference is in X upper star, which says that this expression here is well defined. So the character that you're inducing on the split part, on the A parameter, it's given by nu. And on this product of Z2s, it can be written this way: chi evaluated at this element e to the 2 pi I mu check is this number. You pair rho minus lambda with mu check. And rho minus lambda is in X upper star, and mu check is in 1/2 X lower star. So this number is plus or minus 1. Okay, so that's just a recap of what we did last time, having to do with the principal series. Okay. Now let's, so today I'm going to focus on the opposite case. What do you do? What happens when theta x is acting by 1? That corresponds to the discrete series. So for the rest of today, I'm going to make the assumption that G has discrete series representations. That's not all groups do, of course, but let's make that assumption for today. And I'm going to be given a group G, a complex group G of C, and I'm interested in representations of real forms of it that have discrete series. Well, there's this distinguished involution floating around in the background, and the assumption that G has discrete series is exactly the same thing as saying that this distinguished involution is the identity. So all of this business about the twisting of the group goes away in this case, and everything I say for the rest of today is based on that simplifying assumption. And at some point we'll come back and put the twist back into it. But when you're talking about discrete series, there is no twist. Okay, so this is a basic principle that bears repeating 3 times in red. We have our group, and we've fixed a Cartan subgroup H and a Borel subgroup B, and they're really, really, really fixed. They never vary. The nice thing about this point of view is this fact that you can always work with a fixed Cartan and a fixed Borel, and other things are varying, but that's sort of rock solid. And for people that have, work with representations, it's sometimes it's a bit of a pain if you have different Cartan subgroups and roots, and you have to identify them, and maybe there's a choice of identification and everything. And well, that's not the case here. That's all gone away. So H and B are fixed. And sometimes people ask me, well, which H and which B? And well, the point is you can fix any one, and you should think of them as being the simplest one. H is more or less diagonal and B is upper triangular. That's not necessarily literally true, but that's the idea. It's you pick a convenient H and B. Okay, so having done that, so that's the setup. We have, so you should think as you're being given a group and a Cartan and a Borel. And what I'd like you to do now is take an element XB, B stands for the base point, based element, take an element of G whose square is central. Okay, then you can attach to that is the involution int of XB. Int is stands for is the automorphism given by conjugation by this element. And since the element squared is central, this theta is an involution. And by Cartan's theory of real forms, an involution gives you a real form of G. It's the one, and you then K is the fixed points of this involution, and the relationship is that the real form that you're talking about is the one whose complexified maximal compact subgroup is K. Okay, so that's the usual theory of real forms, a la Cartan. And we're interested in the following space, KGB. There shouldn't be braces on the left side of this formula. We're looking at the space K mod G mod B, and there's a couple of different ways of thinking of it. Well, it's the double coset space as indicated. That's the same thing as saying it's the K orbits acting on the flag variety G mod B. Okay, so now everything here is complex. So G of C mod B of C is a complex algebraic, is a complex projective variety, and K is a complex algebraic group acting on it. And it's a fact that it has finitely many orbits. And well, G mod B is just another name for the Borel subgroups of G. There's a bijection between G mod B and the Borel subgroups of G, and if you unwind that, you see that the space that we're talking about is exactly the same thing as the Borel subgroups of G up to K conjugacy. Okay, Susanna says, I downloaded the new version of Atlas scripts. Now Atlas does not seem to be able to read files like all parameters.at. I don't know what that's about. It should be able to. I'm not sure what you mean when you say it's unable. You get an error message, I suppose. Anyway, let me know what that's about. Okay, so we're talking about K conjugacy classes of Borel subgroups. Okay, so here's the big theorem that's behind the Atlas software. This space KGB is in natural bijection with the following set. It's the elements in the normalizer of H, which are G conjugate to XB, and it's this space modulo conjugation by H. Okay, so this is essentially, well, no, this is, excuse me, not just essentially, this is a finite set. And it's a finite set, subset of the normalizer of H, well, this quotient. It's a finite set once you quotient out by the conjugation action of H. And the map is the following. If X is an element of the right-hand side, by assumption, it's conjugate by G to this base point XB. And so pick a G, which does that conjugation, then this element X goes to the Cartan subgroup G inverse BG, which is to say the K conjugacy class of that Cartan subgroup. So B is this fixed Cartan subgroup. All Cartan subgroups are conjugate. So this G inverse BG could be any Cartan subgroup in G. The conjugation action is, you get every Cartan this way. And the map takes X to the K conjugacy class of this Cartan. Okay? And just for sort of a sanity check that this is well defined, if instead of writing X as G XB G inverse, you could have written it as GK XB GK inverse, where K is in K, which is to say the stabilizer of X. Well, if you did that, then the Borel that you would get would be this one, K inverse. It would be K conjugate to the original one, and these Borels are defined up to K conjugacy. So when you put the brackets in to indicate that, you're getting the same K conjugacy class of Borels. Okay, Brian says, you keep saying Cartan, but don't you mean Borel? Well, I didn't hear what I just said, but probably yes. I must be, of course, I'm talking about Borels here. So the this thing in brackets is a K-conjugacy class of Borel's, and this note is saying that this map that I've defined is well defined on K-conjugacy classes of Borel's. Sorry if I misspoke there. Okay. All righty. So let's. So here's a definition. There's the space X is this space appearing in the theorem. It's the elements of the normalizer of H, which are conjugate to this fixed X, modulo conjugation by H. This is a finite set. And for those of you who might be looking at other sources, this is actually what I usually denote as X with brackets XB. This is the subset of, there's a bigger space X where you run over all strong real forms, and this is just the one having to do with this fixed strong real form. So it's a slight change in notation, and the connection is given by this really statement. But for today, I'm just going to fix this XB and only talking about the subset of elements which are conjugate to that fixed one. Okay, I should maybe say that more slowly one more time. If you look in the algorithms paper, this space that I've defined here is denoted X bracket XB, and the space that's denoted X in the algorithms paper is bigger than this. Okay. All right, so there's an Atlas command, which I will illustrate when I come back to the software, called KGB, which returns a finite set of these so-called KGB elements. All right, so let's look at an example. And I'm going to do the example sort of mathematically here, and then after the break, I'll look at the software. So let's take the group to be SL2C, and take XB to be this diagonal I minus I. Notice that if you square this element, you get minus the identity, which is central. And the stabilizer of this element is the diagonal torus Z1 over Z, which is isomorphic to C cross, which is isomorphic to SO2C. And that says that the real points of this group is the compact form of SO2C, which is SO2. And what's the real form of SL2C that has maximal compact SO2? Well, of course, that's SL2R. And in this incarnation, it's better to think of it as being SU11. Okay, so that's my XB. And it's an entertaining exercise, which you can do in your head practically, which is to say that in this example, KGB has K mod G mod B has 3 elements. There's this element XB, and there's minus XB, and up to, well, not even up to conjugacy. These are all of the elements of the cartan that are conjugate to XB and minus XB. And then there's another element U, which is not in the cartan, but it is in the normalizer of the cartan. And this element is also conjugate to XB. And that's it, up to conjugacy by H. So if you think about it for a moment, this XB and X minus B are both fixed by conjugation by H. H acts by conjugation on U, and in fact, instead of U, I could have put any element of the form 0, Z minus 1 over Z, 0. Those are all conjugate to XB, but they're all, furthermore, they're all conjugate by H. And so after you mod out by conjugation by H, this is the 3 elements. So I'm claiming that a K acting on G mod B has 3 elements. Well, everybody, I hope you all know that this is the usual action of SO2C on the projective plane. It has 3 orbits, 0, infinity, and C cross. So in the picture of Borel's, this XB, well, by definition, it's going to this standard Borel, the Borel we picked way back at the beginning of time. the fixed Borel, and I didn't say this, but if I took it I'm taking it to be the upper triangle, the usual upper triangular matrices. And then what is x minus xb? Well, you have to find an element which conjugates xb to a minus xb, and that is to say it's this Weyl group reflection S alpha. And the new Cartan that you're going to get is S alpha acting on B, which takes you to the opposite Borel. So minus xb is giving you the lower triangular Borel. Okay, and the more interesting one is this element 0, 1, minus 1, 0. You need to choose an element G, which conjugates that to XB. And this is some sort of Cayley transform. You can take it to be this element, for example. And if you do that and you conjugate B by this, what you get is this collection of matrices. So let me go back to the previous page. Where is it? Whoops. The Borel has this Z1 over Z on the diagonal, and the nilpotent part is W. When you conjugate that, you get this guy right here. The diagonal entries go to this, and the W goes to this. And so this is our third, this is a representative of the other conjugacy, K conjugacy class of Borels. And sort of, well, one of the key points here is the following. If you just look at the Cartan now, the Cartan is the Z part of it. You're getting this this Cartan, cosh, sinh, minus sinh, and cosh. And what is this? Well, I've fixed the Cartan involution here to be theta xb, and it's acting by conjugation by this element I minus I. And on this Cartan, it's acting by inverse. You can check that easily enough. This element diagonal I minus I acts trivially on the diagonal Cartan, and it's acting by inverse on this Cartan. And the real points of this Cartan is these matrices cosh, sinh, cosh. And actually, there's also the matrix minus the identity, which I forgot to write down. The real points of this matrix is the split Cartan, R cross, and this is the usual way of writing down the split Cartan in SU11. Okay, so the punchline is here in the box. The point is that this pair, this H double prime with this fixed Cartan involution acting on it, is conjugate by G to the original Cartan and the conjugation action of this element U. And we're doing everything up to conjugation by G. And the left-hand side is the way a human thinks of the split Cartan in SU11. We have a fixed real form, theta, and there are different Cartan subgroups. One of them is compact, and this one is the split one. On the other hand, the software fixes H. It never wants to talk about H double prime because that's a different Cartan. It wants to think about H, and that's okay because when you conjugate H double prime back to H, that's where this theta U is coming in. So in other words, rather than thinking about this split Cartan, it's saying, okay, let's take the fixed diagonal Cartan H and vary theta. Instead of using theta xb, we're going to use theta u, which is acting by -1 on the fixed Cartan. Okay. Oh, I see it's 3 o'clock. I'll go for another 5 minutes and finish these slides maybe and then take a break. Okay. So the moral of the story is, again, the H and the B are always fixed. And you should think of fixing this base point xb and fixing theta to be conjugation by that and fixing k to be the fixed points of that. And now we're going to vary x's in the space x and the corresponding theta x's. And rather than talking about the Cartan subgroups of G, and they're acted out with their action of this fixed theta, and up to conjugacy by K. Instead, we're going to look at just this fixed Cartan H and these different theta x's as x runs over x. So we've conjugated everything back to H, and the cost is, instead of talking about this one theta, we have to talk about this family of theta x's. And similarly for the Borels, instead of talking about all of the different Borels up to conjugacy by K with their action of this fixed theta, we're going to conjugate all those Borels back to the fixed one and vary this, this theta, vary x and the corresponding theta x. Okay. And another important point is that we're going to be talking about GKX modules, and now x is going to vary, and these x's are all conjugate to xb, but they're only conjugate to it. These kx's, and so therefore these kx's are conjugate to this original k, but they're only conjugate to it. They're not literally equal. And so as you vary x, you're getting these GKX modules, but by using this conjugation, you could conjugate them all back to this fixed GK or GKXB modules. And so that's something that's varying at the same time. And just to write down a little formally what we're talking about, if we have a GKX module and a GKX prime module, we're going to identify them, say they're isomorphic, if, well, x and x prime have to be conjugate. So you choose a G which conjugates x to x prime, and then the action of G on pi is supposed to take you from pi to pi prime. Okay, so in this way, the software is varying x. But at the end of the day, if you needed to, you could conjugate everything back to the fixed xb. So let me say a few more things about KGB. So again, we're going to fix this xb, and we're going to take the space x, and we're going to look at this KGB that gives you k, and x parameterizes this space KGB. And in the software, we get this finite set of elements x0 through xn. Or xn minus 1, excuse me. And the Weil group acts naturally by conjugation on x. That's just sort of obvious from the way it's been defined. And what happens is that the quotient of this action gives you the conjugacy classes of Cartan subgroups in your group. And so when I've been talking about having a Cartan associated to an element x, well, that's this statement. There's a map from this space x to the conjugacy classes of Cartan subgroups, and it factors through this quotient by W. And another important fact is that W acts on x, and the stabilizer of an element is the so-called rational Weil group. This last term here I've written, it's the Weil group of the real form with respect to that Cartan. Back in the theta world, you can think of it as being WKH, but maybe it's slightly more familiar to talk about the real Cartan subgroup. So that's something which plays an important role. And finally, there's a map from this space x to the involutions in the Weil group. And well, this map is sort of obvious because this element x is an element of the normalizer of H, so you just take its image in the Weil group, and that's an involution. And this space IW, that should be a script I. This space of involutions in the Weil group, conjugacy classes of involutions in the Weil group, that's what this IW mod W is. That gives you the conjugacy classes of Cartan subgroups in the quasi-split form. So there's a map from X to I, which isn't necessarily surjective. If the group is quasi-split, it is. And so this I is telling you about Cartan subgroups of the quasi-split form. So this is a nice elementary object. It's just the conjugacy classes of involutions in the Weyl group and those parameterized conjugacy classes of Cartans in the corresponding quasi-split group. Okay, so here's a picture extracted from the algorithms paper, which gives an example of this. This is the KGB space for SP4, and it has 11 elements numbered 0 through 10. Those are the black dots. And right here, this row is the involutions in the Weyl group. Whoops. This is the involutions in the Weyl group. There's the identity. There are the two short reflections, alpha 1 and alpha 2 are short roots, and beta 1 and beta 2 are the long roots. And then there's the -1. And the corresponding Cartan subgroup is, well, if the involution is 1, the Cartan involution is the identity, that's the compact Cartan. And the short roots give you the Cartan, which is C cross. These give you the Cartan, which is S1 cross R cross. And -1 is giving you the split Cartan. And what this picture illustrates is the map from KGB to IW. So there are 4 elements which map to 1. And there are 2 elements here, 6 and 7, which map to S alpha 1 and S alpha 2 respectively. And there are 2 elements which map to S beta 1 and S beta 2. And then there's a single element which maps to -1. And again, when we get to the software, I'll look at an example of this. And well, these arrows are Cayley transforms, and the labels on the arrows are telling you there's a Cayley transform by simple root 1 or 2. I'm not going to be, I don't care too much about that at the moment. Okay, so, well, this is a good picture to keep in mind. And so let me say again, what you do is across the bottom, you write the conjugacy classes of involutions in the Cartan, in the Weyl group. And then this KGB space is living above that. And there's essentially, well, there's a finite to 1 map from the KGB space to the Cartan. And you can, it's helpful to think about these fibers in this way. And so, for example, what that says is these 4 KGB elements, 4, 5, 8, and 9, if you use those for the X in a representation, that representation is coming from this Cartan subgroup. So, for example, all of the representations coming from the split Cartan have X is equal to 10. And then after the break, I'll come back and I'll talk about the representations coming from KGB elements 0, 1, 2, and 3. All right, it's a little over an hour. It's a good place to stop. So let me, how do I do this? Let's close this window. Let's go back to the software, which I think is this. No, it's not. Let's go back to software, which maybe is this. No, it's not that either. It doesn't matter. Let's just say having a break. There we go. How's that look? I'm not sure if people are seeing that. Let's do that. Okay. So it's 3:10. I'll come back in 5 minutes. And if there are any questions, post them, please. I'll address them when I come back.